Hello and welcome to Chapter 12, Patterns and Governance Deliver Economies of Scale in ISOL 536, Security Architecture and Design. My name is Dr. Alan Dennis. I'm your instructor. Jumping right into Chapter 12, Patterns and Governance Deliver Economies of Scale. Section 12.1 will discuss the expressing security requirements and the subsections that go over expressing security requirements to enable, who consumes requirements, getting security requirements implemented, why do good requirements go bad. Then in section 12.2, some additional thoughts on governance, and then we'll close with a summary. Jumping right into the first section of chapter 12, a well-known result from rigid standardized processes and heavy governance of those processes is a slowdown in delivery. When due diligence, in other words, security architectures, resources are highly constrained, and there exist rigid processes that require those shared resources to assess everything, due diligence will become a severe bottleneck rather quickly. On the face of it, and simplistically, it may seem intuitive to enable a law and order or command and control process, make everyone behave properly. But anyone who's read the legendary book, The Mythical Man Month, Essays on Software Engineering by Frederick P. Brooks, Jr., uh, and similar studies and essays knows that the more administration and bureaucracy an organization instills, the less work actually gets done. One classical problem is how to deal with systems that will be exposed to the public internet. We know without a doubt that the public internet is hostile and hosts on the public internet will be attacked. To counter this omnipresent attack level, there are typical solutions. We generally use things like firewalls that allow traffic only to designated point public interfaces that will be exposed. Bastion, HTTPS terminating host or equivalents such as a load balancer or virtual IP manager, access restriction to and protection of management administrative interfaces, network and protocol restrictions between traffic terminators and application logic, between application logic and storage or databases, that is multiple tiers and levels of trust. Security configuration, hardening, patching of known vulnerabilities, and similar authentication between layers of the automated processes and between trust levels, and we restrict to and protection of the networking equipment. Management of administrative access to the systems that may be exposed to potentially hostile traffic is fairly well documented body of practice for those architectures in which rigorous management was among the security requirements. In this book, I have consistently cited NIST 800-53 as a reference to the body of practices that would fulfill this requirement. The citation is not to suggest that an organization shouldn't create its own standards, nor do I mean to suggest that NIST standard is the only and only best standard, the one and only best standard. It is simply well known and relatively widely accepted. At this point in information security practice, I see no need to regurgitate these table stake requirements. There isn't much mystery or contention about what robust system management entails. In section 12.1, we talk about expressing security requirements. Applications rarely have clear security requirements over and above the vague injunction to follow all corporate security policies. The architect is left groping in the dark when confronted with the question, does this product support the context in which security appears within my application? Indeed, there is a significant conflict between empowering intelligent, skilled people to be creative and innovative against the necessity to make sure that certain steps are followed, and particularly that the important high priority security requirements get addressed. I believe that it is impossible to simultaneously empower people to think for themselves and also order the same people to do as they are told. When people think for themselves, inevitably they're going to form their own opinions. Even more so, highly capable people, divergent opinions may just be correct. Section 12.1.1 is about expressing security requirements to enable. One of the key skills that can help in writing requirement at the correct level at which the requirement will be consumed. This is often a difficulty for the engineers who are used to expressing a technical matter in much detail as possible. For any but an inexperienced or unskilled implementer, this would be a mistake. There has to be enough specificity that the security requirements can be implemented somehow, that the goal of the requirement can be met. But generally, a requirement shouldn't be written such that it hamstrings the implementation to exactly one particular or narrow implementation. So who consumes these requirements? The maximum for getting requirements to the right level of specificity is just enough to deliver an implementation that will meet the security goals. In this example, the security architect is not really concerned so much with how the restrictions are implemented, but rather that it will be difficult for an attacker to use the terminating network, DMZ, as a beachhead to attack the application server. The security architect is interested in preventing a loss of control of the Bastillion network for whatever reason to cause a loss of the entire environment, starting with the application server. This means traffic to the application server must be restricted to only those systems that should be communicating with it. With traffic originating from termination to application server, neither the other way around. That's the goal. Any networking method employed to achieve the goal is sufficient. Consider a requirement that specified MD5 at a time when it's still considered sufficient protection. Not only would every system that had implemented MD5 be subject to change, but all the requirements specifying MD5 would suddenly become obsolete. What if MD5 were specifically called out in a corporate standard, or even worse, in a policy? In large organizations, policies are only rarely changed and only with approval at a very high level in the organization, often with several stakeholder organizations, for instance, a legal department. In response to the loss of a particular cryptography algorithm that has been specified in a policy, changing that policy and all the requirements to meet that policy become quite an extensive proposition. When requirements cannot be met for whatever reason, a risk analysis will help decision makers to prioritize effectively. It's useful to remember that different stakeholders to a risk decision may need to understand the impacts expressed in terms of each stakeholder's risk. We can cover this topic somewhat in the chapter on risk, chapter 4, although there are many places in the security life cycle where risk needs to be calculated and expressed. Prioritization of security requirements against resource constraints, budgets, delivery schedules remains one of the most common. This is typically a place where the security architect who has a fundamental understanding of risk and organizational risk tolerance can offer significant value. When decision makers have built trust that the security function has a method of rating risk in a consistent and fair manner, they may come to depend upon the risk ratings in their decision-making process. And this is a lot of good material. It's basically letting you know that everything should be done in an informed way and at the right level of detail. Don't be too specific, but don't be so vague that an individual has no chance of meeting the requirements. Section 12.1.3 talks about getting security requirements implemented. So in today's fast-paced, often agile software development, how can the security designs be implemented? In my experience, tossing requirements, architectures, and designs over the wall and into the creative, dynamic pit of agile development is a sure road to failure. Three things must, not mutually exclusive by any means, are likely to occur. Artifacts injected into the agile methodology from outside will be ignored because the documents appear to be irrelevant. Developments, learnings, and changes during development will cause elements to change, even for assumptions to get invalidated, causing security elements to change dramatically or not get accomplished at all. If the Agile team members attempt to adhere strictly to the artifacts brought in from the outside and not directly generated by the Agile process, this blind adherence will cause team velocity and creativity to fall, even to stagnate. It's important that the security assessor has good reason for requirements, data on attack levels, types of attacks, well-known compromises, and the like bolster the reasoning for the requirements. At one job, I learned that our web interfaces received 7 million attacks each day. When I had to drive a web security requirement, mentioning that statistic often removed resistance once people understood that the attack was reasonably certain. A big mistake is to issue a security requirement that forces another group to interrupt the way it works, the flow that has been carefully crafted over time. In the above example, every solution proposed required the IT team to lose some of their efficiency. The ideal solution here is that the agile team includes those security members rather than doing things off on their own. Expressing the overall intent is essential, not the implementation, so that you explain that in this case, the attack was a certainty, not just a certainty, a very large certainty. Is a good way to get people's attention. Follow it up with engagement so that you're actually sharing in the process, helping them in the delivery, helping them in the design as they're designing the pieces they need. And that's a key concept to understand about agile development is you don't design it all at once. You design it as you need to design it. So more likely than not, the security architect needs to be engaged for longer periods during that process. So why do good requirements go bad? One or more requirements may not be implemented as written, possibly not buildable at all. There are many reasons why requirements don't actually get built that have nothing to do with how well the requirements are written. For instance, there may be changes in the business context that cause schedule, budget, or resource shifts, or assumptions that a design has been built upon may turn out to be incorrect, invalidating requirements based upon those design assumptions. That's going to be true of anything, not just security design assumptions. And that's, again, why the security architect needs to be engaged in the entire process. Some additional thoughts on governance. Governance is introduced into an SDL or system delivery process, not to ensure that everything is perfect, but so that these hard decisions don't slip under the radar and are not made for the convenience of those charged with on-time, under-budget delivery. These people have a built-in conflict of interest and may not have the security and sufficient computer risk background to effectively make these sort of decisions. In order to keep high velocity, the governance check has to be very, very lightweight. Eventually, IT people responsible for deployment were given the project list so that the security engagement checks didn't even require a security person, junior or not. It was simply a part of the woodwork. Governance of this nature works best, I think, when it is almost invisible except for those projects that are out of process. And in the certain knowledge that there is a check both of web vulnerabilities engagement, only the very brave or the very foolhardy attempt to end run a process outside of the process. We let everyone know that these checks were in place. Basic idea here is that you have to be considering security the entire time that a project is underway. It's not just that a one sort of thing. Everybody needs to be thinking about it. Also knowing that at the end of it all, that programmatic testing is going to be done against the code. Make sure that the people actually developing the code do it the right way because they know that there is going to be a security review. And in fact, they may want to do that testing as they go. So as they reach these milestones during their development of sprints completing, they may, as part of their artifacts of that and their procedures, test the stuff out and see how it's doing. That gives them a chance to fix it as they're going rather than have to rework it later on. With that, we've reached the summary for Chapter 12. Where there is resistance, having concrete examples helps stakeholder understand the reasoning that gives birth to security requirements. Sometimes a single pithy statistic or a particular attack example will help others jump on the security bandwagon. For those instances in which there is outright resistance, identifying what is being protected or some other solvable pain point can turn enemies into allies. No matter what happens in complex, highly dynamic organizations, there must be some governance that security requirements are being fulfilled. This is necessary even when there is a great deal of security buy-in because there always seems to be at least one clever person who will attempt to shortcut the delivery. There has to be a method that catches these attempts even when they are rare. Otherwise, the defense of other systems may be impacted. There's a due diligence responsibility to ensure that the requirements are met and risks are raised to decision makers. So if you're going to bypass the system, make sure it's done in a knowing way and with an exception, not just somebody going off and doing their own thing. With that, we've reached our conclusion of the discussion of Chapter 12. As always, if you have any questions, feel free to reach out. That's what I'm here for. Stay safe, and we'll speak again soon.